Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 38, and this question is asking us, starting from this starting material, how can we convert this to the following products and identify the reagents that we have to use. So let's draw the starting material we're given. So we have this alkyne bond, central carbon, another carbon, then we have two ethyl groups coming out of it. And then for A, we're trying to generate something that has a ketone, carbon, carbon, and then those two carbons here. So let's count our carbons, see if there's any change in number of carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. In product, we have 1, 2, 3, 4, 5, 6, 7, 8. So no change of carbons, but what we have is a ketone on carbon 2, so right here. So how can we do that? Well, we know that we need to reduce this alkyne to a ketone, or to an alkane with a ketone. So how can we do that? Well, we need to use the pi bond electrons in this alkyne to act as a nucleophile. So what is the electrophile that we need to attack? Well, we're trying to get an oxygen here, so it has to have and contain oxygen. So that means we can just use water. But now we need something to protonate the system to make sure it's acidic water. So we know that water needs to exist in equilibrium with H3O+, the acidic version of water. And the only way we can do that is adding any strong acid, such as an HA, which is H2SO4. So if I were to do that, we know that following Markovnikov's rule, we'll pick up a proton on the side with the most number of protons, and then we would form an intermediate that has a carbocation here on the secondary carbon, and we have our OH2 that can nucleophilically attack this to now form an oxygen bond on the second carbon of this structure, which is exactly what we want. And then once our A- deprotonates this, because oxygen would have 3 bonds, but then A- picks up one of those protons, we're left with an alcohol. So now we see that we have an enol form of a potential tautomer. So if we add mercury, so you have to remember these reagents, these combinations. So water, acid, and mercury, we can get keto enol tautomerization, so we can form a keto version of this molecule by using one of those lone pair of oxygens to come down, make a carbonyl group, make a new bond. When you make a bond, you break a bond. So there would be an extra proton added on this side. And we have our final structure here. So these are the reagents we have to use for A. Now for B, we're trying to form something that has, once again, a carbonyl, but now it's an aldehyde. So we have carbonyl, carbon, 2, 3, and then those two ethyl groups coming out of it. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the number of carbons didn't change. So how would we do this? So now we are trying to get a carbonyl group here, but now it's going to be on carbon 1. But how can that be possible? How can we add or get a carbocation intermediate on carbon 1? Because this would produce, if carbocation was here, this would be a primary carbocation and less stable than a secondary carbocation. So we know that secondary would occur and not primary when we react with some sort of electrophile with this starting material. But we have a trick up our sleeve. So we know that from the previous problem, 36, we know that if we add boron, boron will add to the least substituted side because it's so bulky itself. So remember, I like drawing BH3 as BH2 bond H, and I like drawing it in such a way that the boron is directly on top or underneath the side with the more protons on your alkyne or alkene even. So I know that there'd be sigma bonds being formed here, and then when you make bonds, you have to break bonds. So the bond I'll break is this bond and one of these. So what would be the intermediate product of that? So let's draw the intermediate products of this. So BH2, but now we need to convert this BH2 to aldehyde. So how do we do that? So remember from problem 36, I told you guys that we had some sort of oxidizing agent with base. And the mechanism of this is beyond the scope of any introductory level in organic chemistry course, but you need to know when you add some sort of oxidizing agent, this BH2 gets oxidized to a carbonyl group. And then when you form a carbonyl group, you can imagine you're adding a new bond here. So this carbon essentially would have 5 bonds, but that's not possible. So then obviously this pi bond here would have to break. So then now we're left with an aldehyde. And sorry, let me count my carbons better. You're left with an aldehyde. So that's B. Now for C, we have, let's draw it out on the next page. So we're starting from this. And we're going to this. Let's count our carbons. So we are in our starting material of 7, and we have 1, 2, 3, 4, 5, 6, 7 in the product as well. So now we see that we add 2 halides, this halide being chlorine, on carbon 2 right here. So how can we do that? Well, on this side, initially we start off with 1 proton, but in this final product, on carbon 1, we have 3 protons now. So we know that we need some sort of HX, some H halide, in this case HCl, to form this product. So if I add 1 equivalent to HCl, we know following Markovnikov's rule, the nucleophilic alkyne will pick up one of those protons on the side with more number of protons, being carbon 1. Now this side has 2 protons, giving us a secondary carbocation in which the chloride ion can attack, being nucleophilic itself. And carbocation center is very electron poor, so acts as our electrophile. So now we see we have one of these chlorine ions here, but we still have an alkene bond here. Well, in the product we have an alkane. So what we need to do is just add a second equivalent of HCl. So you need 2 equivalents of HCl for this problem, and the same thing would occur to yield your final product like this. Last question. Oh, so here we're actually adding carbon. So let's draw the starting material product for this. Oops. So we have here we see that we have the same structural shape on the left side up until this alkyne, but after the alkyne we add 2 more carbons. So what does that mean? That means that we need to make our alkyne into a nucleophile so we can attack 2 carbon and a 2 carbon electrophile. So let's draw 2 carbons and let's add a good leaving group for this electrophile to make it into electrophile. So we can add any halide, bromine, chlorine, iodine, fluorine, whatever it is. We have 2 carbons, a good leaving group. So now we have an electrophilic compound for step 2. But now we need to make this alkyne into a good nucleophile. So as you saw from previous problems, we can make this a good nucleophile by taking away this acidic proton. So we can add some sort of proton abstracting agent like sodium hydride or NH2 minus or something like that takes away this 1 proton to make hydrogen gas, neutralizing this hydride. And then you would make a carbo ion intermediate. So after step 1, you'll form a carb anion intermediate with those 2 extra electrons, so it acts as a nucleophile, and it'll pick up your electrophile, making a bond. You make a bond, you break a bond. That's why we added this halide to act as a leaving group. Then we form our final product here. So this can either be sodium hydride or NH2 minus, anything that can rip off one of those protons. Obviously, it'll form hydrogen gas in this case, or ammonia in the case above, once you pick up that extra proton.